Okay, let's look at dissociation equations and solution conductivity. So in the warm-up, it says, if you are a coffee drinker, you've experienced the effects of dilution and concentration. Assume you are making yourself a cup of coffee. Describe how you would make a strong cup of coffee. Well, you would probably use more coffee grounds to get a stronger cup, or you would use less water. Number 2, if you wanted to dilute the coffee in your cup, what would you do? Well, you could use more water, or you could add more creamer. Number 3, when you dilute the coffee, have you changed the amount of caffeine present in the cup? Explain. No, you haven't, and that's because you simply increased the volume of the solution. So you didn't add more coffee grounds. So we're going to be talking about diluting solutions. And molarity is the amount of solute in moles in a given volume of solution. And when you add water to a solution, the concentration decreases, and we say that the solution is diluted. The opposite of diluted is concentrated. And to make a solution more concentrated, you could evaporate some of the solvent, or you could remove some of the solvent from the solution. You could also add more solute to the solution. The brackets around a chemical formula indicate molar concentration, which is moles per liter. For example, if you have, what is the new HCl in brackets? That means what's the new molar concentration of HCl? And if you take a look at the dilution equation here, it says you have a 15 milliliter sample of 3 molar HCl diluted by adding 10 mils of water. So the initial volume is 15 mils, the initial molarity is 3 molar, and then you're adding 10 milliliters of water, which means you're going to a final volume of 15 plus 10, which is 25 milliliters. So 25 milliliters is going to be your final volume. And they want to know what the new concentration is, so we're solving for M2. Now, anytime you're doing a dilution, so it's the same solution and you're adding water to it, you're going to be using an equation M1 times V1 equals M2 times V2. And that's because you're going to take the initial molarity times the initial volume, that equals the final molarity, M2, times the final volume, V2. Now, you only need to make sure that your units for volume match. They can both be milliliters, they can both be liters, it doesn't matter. And you would simply substitute. They do a lot of other things here that I feel is just not necessary. So what you're going to do is you're just going to put your 3 molar here into M1, and your V1, which is 15 mils, would go there. And then you're solving for M2. Let me fix that. And then your V2 is 25 milliliters. So that means that you're going to divide both sides by 25 to solve for M2, and you're going to end up with 1.8 molarity. So we're going to apply this on the next page in dilution calculations. So if you take a look at number 1, it says a 50 milliliter sample, so this would be your V1, of 0.1 molar NaOH, which is M1, is diluted by adding 30 mils of water. So if we're adding 30 mils of water, 30 plus 50 to get my V2, is 80 milliliters. And they want the resulting NaOH concentration, which is M2. So this is going to be M1 times V1 equals M2 times V2. If I'm solving for M2, you want to divide by V2 on both sides. So this is M2 equals M1 times V1 divided by V2. So your answer will be 0.0625 molarity. Okay. Now for number 2, it says you have a 35 ml sample. So this is my V1 of 1.5 molar H2SO4, which is M1, and it's diluted to 50 mils. So that means that your V2 is 50 mils. What's the final concentration of H2SO4? So again, we're solving for M2. So your M2 is going to be M1 times V1 divided by V2. And this is going to be 1.05 molarity. Number 3, a student dissolved 0.25 grams of calcium nitrate in 100 mils of water. Let's just start with that much. So we're probably going to be converting grams to moles and dividing by the 0.1 liters to give us a concentration, because 50 mils of that solution is diluted to 75 milliliters. So that means that you're going to a final volume of 75 mils for your V2. They want to know the final concentration, so we'd be solving for M2. So we need to start with the 0.25 grams of calcium nitrate, and we've got to convert that to moles. Which is 164.09 for the molar mass of calcium nitrate. Grams will cancel. You will get 0.00152 moles of calcium nitrate. Divide that by 0.1 liters, which is going to give you 0.0152 molarity. Now, they took 50 mils of that concentration. So that means that this is my M1, and they're taking 50 mils of that, which means this is my V1. So when you solve for M2, this is going to be M1, which is 0.0152, times V1, which is 50 milliliters. Divide that by V2, which is 75 milliliters. And then that's going to give you 0.010 molarity for the concentration. One last problem, number 4. Calculate the concentration that results, so that means we're solving for M2, when 18 mils V1 of 0.4 molarity M1 is added to 20 mils of water. So that means your V2 is going to be 20 plus your 18 milliliters. So this is going to end up being 38 milliliters for V2. So your M2 is M1, which is 0.40 molarity, times my V1, which is 18 milliliters, divided by V2, which is 38 milliliters, and you will get 0.189 molarity. Okay, let's talk about ions in solution. You know that water molecules are polar. They have a positive end and a negative end, and depending upon the ion that they are surrounding, whether it's a cation or an anion, if it's a cation, you know that that's going to be attracted to the negative end of water, which is the oxygen end, and if it's an anion, it's going to be attracted to the positive end of water, which is the hydrogen end. So solids dissolve in water by separating into their ions, and solvation is the process where the solvent molecules surround the solute particles, or the ions that are in a salt, for instance. And when the solvent is water, we call it hydration. A dissociation equation represents the process of the positive and negative ions in the salt being separated by the solvent. And if you look here at percent ionization describes the extent to which a given acid's molecules are ionized. So in other words, if it's a strong acid, it completely ionizes and it's 100% ionized. If it's a weak acid, it's not going to be 100% ionized. It would be much less than that. When you're looking at HCl, which is hydrochloric acid dissolving in water, its ionization equation is given here, where you have hydrochloric acid dissociating into hydrogen and chloride ions. If you have a salt like calcium chloride dissociating, you're going to form a calcium ion and 2 chloride ions. And you have to make sure that you balance the number of ions that are being formed on the product side with the number of ions that you have on the reactant side. So let's take a look at the quick check on the next page. So if you look at number 1, it says write a balanced dissociation equation for the salt when it's dissolved in water. So if you have aluminum nitrate dissolving in water, you're going to form an aluminum ion. And then since you have a 3 subscript outside of this NO3, that means you're forming 3 nitrate ions in solution. And then for number 2, ammonium sulfate, you're going to form 2 ammonium ions in solution and a sulfate ion in solution. For number 3, potassium chromate, this is K2CrO4. And you're going to form 2 potassium ions in solution and then 1 chromate ion in solution. Number 4, zinc phosphate, which is ZN3PO42. When this dissolves, you'll have 3 zinc ions forming, and then you'll have 2 of these phosphate ions forming. Okay, let's take a look at calculating concentration. If you have the concentration of the original solution, for instance, here I have a 1 molar sodium chloride solution. When it dissociates into its ions, you look at the coefficient in front of each ion and you multiply the coefficient by the original concentration of the solution. So to get the concentration of sodium ions, it would be 1 times 1 molar, which is why sodium ion concentration is 1 molar. The chloride ion concentration would be its coefficient 1 times the original concentration, which is 1 molar, to give you a 1 molar chloride ion concentration. Now, what if I had a calcium chloride solution and its original concentration was 1 molar, and then you wrote the dissociation equation? You have 1 calcium ion and 2 chloride ions. So the concentration of calcium ions in solution would be 1 times 1 molar to give you a 1 molar calcium ion concentration. And then the chloride ions would be 2 times 1 molar, which would be a 2 molar concentration for the chloride ions. Now, if I look at the quick check, and we calculate the concentration of all the ions in each of the following examples. So first we've got our zinc nitrate solution, which is going to form a zinc ion and 2 nitrate ions. If the original concentration is 3 molar and I have 1 zinc ion, 1 times 3 would be 3 molar for my zinc ion concentration. And then 2 nitrates times 3 molar would be a 6 molar concentration for my nitrates, okay? If I'm looking at number 2, I'm going to form 2 sodium ions and a carbonate ion. 2 times the original concentration of the solution, 0.5, is going to give me 1 molar. for the concentration of my sodium ions. I have one carbonate ion times 0.5, so 0.5 molar is the concentration of carbonate ions. Number 3, ammonium oxalate. Ammonium oxalate is NH4 in parentheses with a subscript 2, C2O4. You're going to form 2 ammonium ions and 1 oxalate ion. And if this original concentration is 1.5 molar, then 2 times 1.5 will give you a 3 molar ion concentration for the ammonium. And then 1 C2O4 times 1.5 means the concentration of the oxalate is 1.5 molarity. Now, for number 4, calcium phosphate. Calcium phosphate will dissociate into 3 calcium ions and 2 phosphate ions. The original concentration is 3.2 times 10 to the negative third. You need to take the coefficient on calcium, multiply it by 3. 3 times 3.2 times 10 to the negative third molarity. So the calcium ion concentration is 0.0096. 2 phosphate ions times 3.2 times 10 to the negative third molarity will give you 0.0064 molarity for the concentration of phosphate ions in that solution. Okay, now let's talk about dissociation and dilution. Another example of a dilution is when you have 2 solutions that are mixing together. And the resulting solution is going to have a larger volume. And let's take a look at the next page. If we take a look at number 1, for instance. So here it says, calculate the concentration of each ion in the following solutions. Assume that no reactions occur. So if you have a 35 milliliter sample of 0.2 molar HNO3, and you add that to 75 milliliters of 0.15 molar aluminum nitrate, we need to figure out what the concentration is of each ion after the dilution. So that means you're going to do the nitric acid and then the aluminum nitrate separately, and then you would combine similar ions after you get their concentration. So let's see what the concentration of HNO3 is after the solutions are combined. So you've got a 0.20 molar HNO3 solution. Multiply that by the volume in liters of the HNO3, which is 0.035 liters. Divide that by the volume of the solution, which you get by combining your 35 mils in liters plus this 0.0750 liters, which is going to give you 0.11 liters of solution. So you're going to take that total volume and you will put it here. And that will give you 0.0636 molarity for your HNO3 after the dilution, okay? Then what you're going to do is, since HNO3 dissociates into hydrogen ions and nitrate ions, and this is the concentration after the 2 solutions are mixed together. That means that the hydrogen ion concentration, if this is 0.0636 molarity, the hydrogen ion concentration is also 0.0636, and the nitrate ion is 0.0636. Okay? Now I'm going to go ahead and do the aluminum nitrate. So for my aluminum nitrate, concentration after the solutions are mixed, this is 0.15 molarity. I'm going to multiply that by its volume, which is 0.075 liters. And then you're going to divide that by the total volume of the solution, which is 0.11 liters. Okay? And if you want that molarity, it is 0.102 molarity for the aluminum nitrate. Okay? And since aluminum nitrate dissociates into an aluminum ion and 3 nitrate ions, if that concentration is 0.102 molarity, the aluminum ion concentration is also 0.102 molarity. And the nitrate ion would be 3 times 0.102. So this is going to be I want to say it's 0.3, but that seems a little bit. Let me double check this. 3 times 0.102, 0.306 molarity for the nitrate ion concentration. Now, the ion that was shared by both solutions was the nitrate ion. So I'm just going to highlight that in red here. You have a nitrate here, and you had a nitrate right here. Okay? So what you want to do is to get the total nitrate ion concentration, you would combine 0.0636 with 0.306 to give you that total concentration. So that would be 0.3696 molarity for the total nitrate ion concentration. I'm not doing a very good job at following sig figs here. I was, I think, or maybe I wasn't up until this point, but okay, now these problems are a little lengthy, so let's take a look at another one. Let's take a look at number 2, okay? So in number 2, you're combining sulfuric acid with sodium sulfate. So I'm just going to jump straight into calculating the concentration of H2SO4 after the 2 solutions are mixed. The concentration of H2SO4 is 0.85 molarity. Its volume is 22.6 milliliters, so I'm going to convert that to 0.0226 liters. And then the total volume is 22.6 plus 35.4, which is going to give you 58 milliliters. So I'm going to convert that, which is 0.058 liters. And this will be 0.327 molarity. So when H2SO4 dissociates into 2 hydrogen ions and 1 sulfate ion, this concentration is the concentration of the diluted solution, which means the hydrogen ions would be 2 times 0.327. So that's going to be, I don't even know if I have that written here. Let's do this. 2 times 0.327. This is 0.654 molarity for the hydrogen ion concentration. And the sulfate ion concentration will be the same as the original concentration of the solution because there's only one of those ions. Okay? Now, to do the Na2SO4, its concentration is 1.3 molarity. Its volume is 0.0354 liters. Divide that by the total volume, which is 0.058. and then that will be 0.793 molarity for the diluted concentration of sodium sulfate. Sodium sulfate dissociates into 2 sodium ions and 1 sulfate ion. So if the original concentration was 0.793 molarity, or for its diluted concentration, 2 times 0.793 will give you a sodium ion concentration of 1.586 molarity, and then the sulfate ion concentration is 0.793 molarity. Okay, now if I need to get the concentration of the ion that was shared by both solutions, which is your sulfate here, you have to add those together. So the total sulfate ion concentration is 0.327 plus 0.793. And you get 1.12 molarity. Okay, so the other 2 problems, number 3 and number 4, are just like this. So we're going to move on to electrical conductivity of solutions. Okay, now, when electric charge is carried through a solution, we say that the solution conducts electricity. Let me move this over just a little bit so we can get, I should probably bring this down. There we go. Okay. And if a compound's aqueous solution conducts electricity, we call it an electrolyte. And if it's a good conductor, then the compound is a strong electrolyte. If it's a poor conductor, then the compound is a weak electrolyte. And if the aqueous solution of that compound does not conduct electricity, then we say it is a non-electrolyte. Electrical charge is actually carried through the solution by the movement of ions, so you have to have freely moving ions to conduct electricity. Some questions related to this topic will trick you. If you're looking at a solid ionic compound, they do not conduct because the ions are not freely moving. But if they say molten, if it's a molten ionic compound, that means it's melted. That means technically the ions are freely moving. So I'm just giving you that little information. And if the ionic compound is dissolved in water, then the ions should be freely moving and carrying an electric charge. And it tells you here that the charged ions must be free to move in the solution in order for it to conduct. Okay, now positive ions will move towards the negative electrode, and negative ions will move towards the positive electrode, and it's the movement of these ions that completes the electrical circuit. So the more ions that you have present in the solution, that means the greater the conductivity. Typically what we do is we take a light bulb apparatus, and ours tend to have a battery in them, and it's a really simple piece of equipment that we use to test for conductivity. And testing for conductivity is a very just simple concept to determine what we're looking at. So, and whether the substance is actually forming ions or whether it's staying as a molecule in solution. So this is something that you need to understand how to do. It's something that you should be able to pull out and say, oh, I would test for conductivity to see if the compound is made of ions. Is it ionic or is it molecular? Okay. So what happens is when you put the electrodes into a solution, the light bulb may turn on, may glow, if this is an electrolyte solution. So it will be brighter when you have more ions in the solution, because that means there's more conductivity. And if there aren't many ions in the solution, this will be a dim light bulb. And if there are no ions whatsoever, the light bulb will not light up at all. So down here, they give you a little bit more information on specific types of solutions. So a non-electrolyte solution will have no ions to carry the electric charge. A lot of covalent and molecular compounds are non-electrolytes. Some covalent substances do form ions, so they consider them to be strong or weak electrolytes, and they've noted some of the exceptions. All salts are ionic, so they are electrolytes. There are ionic solids that have low solubility in water, so they produce few freely moving ions, so therefore they have low conductivity. But a melted liquid of an ionic salt, this is where I mentioned molten ionic compound, will also conduct electricity. But if you're just looking at an ionic solid, it will not. If you stick electrodes in table salt, it doesn't conduct because the ions are not freely moving. Those ions are locked in place. Now, let's talk about acids and bases for a minute. Acids and bases conduct electricity as well. And the formulas of most acids only contain nonmetals, so they don't appear ionic, but acids release hydrogen ions. So some acids will dissociate completely in solution, and these are strong acids. They're 100% ionized. Other acids contain molecules that mostly remain intact, so that means that there's a small percentage that are dissociating, and these are known as weak acids because they do not form many ions. Water is an example of a molecular compound that dissociates to a small extent. They're showing you here what water dissociates into. And the concentration of hydrogen and hydroxide ions is only 1 × 10⁻⁷ molar each. So water is a poor electrical conductor. Organic acids, are compounds that contain carbon, hydrogen, and oxygen. They contain a carboxyl group on the end of their formulas. It's a COOH. These substances are not ionic, but there are a few molecules that will release hydrogen ions from this group. The one that you need to know is acetic acid. Acetic acid, CH3COOH, we typically write it this way as HC2H3O2. They're showing you that it dissociates into a hydrogen ion and the acetate ion, which is C2H3O2 -1, written in a different way. So acetic acid is a weak acid, which means it is a poor conductor of electricity because it only produces very, very few ions in solution. And acetic acid is found in vinegar. So that's why vinegar is considered a weak electrolyte. Okay, the table on the next page summarizes some common acids and bases. It is probably easiest if you simply memorize this table. So here are your strong acids listed that dissociate 100%. Here are the strong bases that dissociate 100%. Here are the weak acids, and here is the weak base, ammonia, and the weak acids and bases they dissociate very little. Now let's take a look here at the quick check. How can you tell from a substance's formula if it's ionic or molecular? Give 2 examples of an ionic compound. So ionic compounds contain a metal plus, or I should say, this should be an or, the ammonium ion, and a negative ion, an anion. So an example would be sodium chloride, NaCl, because this is a cation and an anion, and sodium is a metal. Or you could use ammonium hydroxide or ammonium chloride. This is the ammonium ion, and then chloride has a negative charge, which is an anion. So that would also be an ionic compound example. I'm waiting for this to focus again. Now, molecular compounds contain nonmetals, and I'm going to change my pen here because this one's not showing up very well. Okay. The exceptions to this is going to be acids and bases. Now, number 2, sugar has the formula C12H22O11. Will a sugar solution conduct electricity? Explain. So this is made of nonmetals. It's a molecular compound. Molecular compounds do not form ions when they're dissolved in water. So the answer would be no. It's a molecular compound and doesn't form ions in solution. Number 3, explain why a 1 molar solution of HCl will be a stronger electrolyte than a 1 molar solution of CH3COOH, which is acetic acid. Okay, acetic acid is a weak acid, so it's not completely ionized, whereas HCl is a strong acid, which is 100% ionized. So 1 molar HCl is 100% dissociated, and 1 molar acetic acid dissociates very little. So you're going to have a lot of freely moving ions in hydrochloric acid, and you would have few moving ions with the acetic acid, which is why hydrochloric acid is a stronger electrolyte. Let's move on to some of the key points of electrical conductivity of solutions. Okay, electric current is carried through a solution by ions. The more ions there are, the higher the solution's conductivity. For the next one, soluble salts and soluble hydroxides dissolve in water to make aqueous solutions with high ion concentrations and consequently high conductivity. Salts with low solubility and hydroxides with low solubility will have low ion concentrations and therefore low conductivity. Molecular compounds do not form ions in solution, therefore they do not conduct electricity. The exceptions are acids and bases. Strong acids and bases ionize completely in solution. Weak acids and weak bases ionize very little in solution.